All right, so we have the notes for section 5.2, proving trigonometric identities. So proofs eventually are true statements. The proof part of it is showing that the two sides are equal. So these are similar to like a two-column proof in geometry, where you're given a given statement and a proof statement. So you're about to use algebra rules, etc., all those things to prove their equivalent. So it says prove the algebraic identity x squared minus 1 over x minus 1 minus x squared minus 1 over x plus 1 is equal to 2. So we need to transform one side of the equation into the other. Now, it's usually easier to start with the more complicated and try to simplify it, as opposed to taking the simpler side and make it more complicated. So the only thing I can do over here is I can try to combine these two fractions. And I do that, I need a common denominator. So the fraction on the left needs to get multiplied by x plus 1 on top and bottom, and the fraction on the right needs to get multiplied by x minus 1. So we have this. So we got, let's see here, x plus 1 times x squared minus 1 over x plus 1 times x minus 1 minus so we have this. Now, what I can do is, if you look on the bottom here, I'm actually going to FOIL these two together because they're a difference of squares. So in the denominator, I'm going to have x squared minus 1 over here. X squared minus 1 times x minus 1 over x squared minus 1. Now, strictly speaking, there is still the equals 2 over here, because that's what we're proving. Now, what I can actually do is, since I have x squared minus 1s on tops and bottom now, I can actually cancel those guys out, which leaves me x plus 1 minus x minus 1 equals 2. So x plus 1 minus x plus 1 is equal to 2. Distribute the negative. X is canceled. 2 equals 2. We have a true statement. So we proved the identity. We showed that the two sides were equal. So down here we got some general strategies. Begins with the expression on one side. Proof ends with the expression on the other side. So I began with this side and turned it into that side. The proof in between consists of showing a sequence of expressions, each one easily seen to be equivalent to the preceding expression, which means you can't make random jumps and substitutions that don't make sense or do multiple substitutions at once. Okay, so now we have a trig identity. So we have tangent plus cotangent equals secant cosecant. Now, when you have a lot of trig functions, sometimes a good place to start is to turn everything in terms of sines and cosines, because all of the trig functions can be written in terms of sine and cosine. For example, tangent is the sine divided by the cosine. Cotangent is the cosine divided by the sine. Secant is 1 over the cosine, and cosecant is 1 over the sine. Now I have a single, actually technically I have a single term over here because they're only separated with multiplication. So over here I need to add these two terms together in order to get down to a single term. So I need a common denominator, so multiply this one by sine on top and bottom, the other one, and this one by cosine on top and bottom, the other denominator. So this fraction becomes sine squared x over sine x cosine x. This fraction becomes cosine squared x over sine x cosine x. And over here, sine x cosine x. Common denominator, which means I can combine the two fractions, so sine squared x plus cosine squared x equals sine x cosine x over here. Now, this is Pythagorean identity. It's equal to 1. And I have my two sides of the equation equal to each other. So they are true. Now, what I could have done is I could have left this as secant cosecant, and then here I'd reciprocal both of those and turn them back into secant cosecant. But as long as once you have the two sides equal, you're done. So some more general strategies, begin with the more complicated expression and work towards the less complicated expression. So I worked on this side because it was more complicated and tried to make it look like this side. If no other move suggests itself, convert the entire expressions into being one involving sines and cosines, which is what I did. I mentioned that everything can be terms in terms of sines and cosine. And combine fractions by combining them over a common denominator. So typically you want to collapse things down. Now, one thing you are not allowed to do on a proof is to move things across the equal sign. So like I couldn't multiply everything by sine, cosine, and cancel everything out. For a proof, the two sides have to remain separate. All right, let's see here. Match the function 1 over secant x minus 1 plus 1 over secant x plus 1 with one of the following, then confirm the match with the proof. So doing the match, I can actually, well, here, we'll work backwards. We can look at the graphs mostly to see which one matches, but we'll just work with this. So I got two different fractions, so I need a common denominator, so they get multiplied by the other denominator. So this one gets multiplied by secant x plus 1. And this one gets multiplied by secant x minus 1. So common denominator means I can combine. So secant plus secant, so this is 2 secant x, and the ones are going to cancel, plus 1, 1 plus negative 1. And on the bottom, I actually have secant squared x minus 1. So it looks like this. So secant squared x minus 1 is probably a version of one of the Pythagorean identities, but I have to figure out which one it is. So to get secant, I need 1 over the cosine, so you divide everybody by cosine. So that's going to be tangent squared plus 1 is equal to the secant squared. So move the 1 over. Secant squared x minus 1 is equal to the tangent squared. So this stuff on the bottom is the tangent squared. So I have 2 secant x over the tangent squared of x. So let's see here. What can we do? Let's turn everything into sines and cosines. So the thing here, well, before we do that, that tangent on the bottom is the same thing as a cotangent squared. I can do the reciprocal. So this is 2 times 1 over cosine x times cosine squared x over sine squared x. Everything in terms of sines and cosines. So this cosine can cancel one of them out here. So I have, let's see here, 2 times cosine x over the sine squared of x. So that's the same thing as 2 times cosine x over sine times 1 over sine. 2 times the cotangent times the cosecant, which looks like that one. All right, last one here, prove the identity. Or not, maybe not the last one. Nope, not the last one. So let's see here. So I can't do cross products, which is what I normally do if I have two fractions equal, because I can't work across the equal sign. So what I'm going to do instead is I'm just going to work on this side. Now, just as a hint, if you see like a 1 minus trig function, or a trig function minus 1 or plus 1, you want to multiply by the conjugate. So this fraction over here is going to get multiplied by 1 plus sine t. The reason I do that is that probably that's going to give me a Pythagorean identity that I can use. And over here, we're leaving this side alone for now. So on the top, I just have 1 plus sine t times cosine t. If you notice, there's my 1 plus sine t. It showed up now. On the bottom, I have 1 minus sine squared. Now the thing is, 1 minus sine squared is a version of one of the Pythagorean identities. It's actually the cosine squared. So I have 1 plus sine t times cosine t all over cosine squared. So I'm here. Now here, this cosine can cancel the squared out, so I'm left with 1 plus sine t over cosine t equals 1 plus sine t over cosine t. So once again, the trick for this one is if you see, and you could have done it over here, you can multiply you see 1 plus or minus a trig function or trig function plus or minus 1, you want to multiply the top and bottom by the conjugate, because that'll force it into typically one of the Pythagorean identities that you can then use to get rid of two terms and make them just a single term on the bottom. All right. So, yeah, this is what I was talking about. Multiply it by the conjugate to set up applications of Pythagoras. Their target expression in favor of manipulations that bring you closer to your goal. So don't just randomly try things. Okay, so here we've got cotangent squared over 1 plus cosecant u equals this stuff over here. So we're going to do our conjugate step on this side. So we got cotangent squared u. We're going to multiply by the conjugate. So this is going to be 1 plus cosecant u, 1 minus cosecant u. And I haven't done anything over here, so we're going to leave these guys alone. So this becomes the cotangent squared of u times 1 minus the cosecant u, all over 1 minus the cosecant squared of u. So 1 minus cosecant squared. So that's a version of one of the trig functions. So sine squared, let's figure out which one it is. So there's my Pythagorean. To get cosecant, I need to divide everything by sine. So 1 plus cotangent squared is equal to the cosecant squared. So this is just, if I bring the 1 over, is equal to the cotangent squared. So I have cotangent squared u times 1 minus cosecant u all over the cotangent squared of u. So over here, those can cancel, so I'm left with 1 minus cosecant u. But that's not what I have on the right, so now let's look at the right-hand side. So if I distribute, I get cotangent u, secant u, minus 1. Because cotangent times tangent, they're reciprocal. They're 1. So, cotangent is cosine over sine. Secant is 1 over the cosine. So those can cancel. It gives me 1 over sine u minus 1, which is the cosecant of u minus 1. But we're not quite the same thing. This is probably like, let's see, cotangent secant. Let me check my work real fast. Oh, there's my problem. My substitution here was wrong. This should be -1, because cosecant squared minus 1 is cotangent, but that's the opposite order. So there should be a negative down there, which means there should be a negative sign out front here. So a negative sign out front here, which if I distribute the negative, gives me cosecant u minus 1, which is cosecant u minus 1. I used this identity when I shouldn't have, because I have 1 minus cosecant squared, so I have the opposite order here, which means this has to be the opposite. So be careful. That's the end of the section.